In this lesson, we're asking what special relationship exists between two lines or a line segment and a line. We know two of the special relationships. We could have that the lines are parallel, or we could have that the lines are perpendicular. In the next part of this lesson, we're going to take a look at the relationship that exists between the distance that you can measure between a line and a point that is not on the line. The shortest distance theorem states that the shortest distance from a given line to a point that's not on the line is the length of the segment that's perpendicular to the line through the point. So let's see what we mean with this example down here. I have line AB, and I also have a point C that's not on the line. Well, this theorem tells me that the segment that's perpendicular to AB and which intersects with C, so I have that segment right there, well, its length, and we can call it CD, is the shortest distance between C and the line AB. Let's prove the shortest distance theorem. We are given a point here, C, and it's not on the line that we're given, which is line AB. And what we need to prove is that the shortest distance from C to AB is the length of the segment that's perpendicular to AB and goes through C. So let's start actually by drawing a perpendicular line segment from C to the line. So I can go like that, and we'll call the intersection point D. Now, the reason we're able to draw such a line is by using some reasoning with the unique line postulate. We need to show that it's the shortest such line segment, the shortest line segment that goes from C to the line. Well, in order to do that, we're actually going to take another line segment that goes from C to the line. And I can draw it like this, and we'll call that intersection point E. What we need to know is that the length of CD is shorter than the length of CE. Well, I was able to draw that line segment CE by the unique line postulate again, and I want you to notice that triangle ECD is actually a right triangle, and that's by the definition of a right triangle, and furthermore, CE is the hypotenuse of that right triangle, and that's because it's opposite the right angle, which means that by the definition of the hypotenuse, we know that this is the case. We know something about the hypotenuse of a triangle. In fact, we know that it is the longest side of the triangle. And so that means that CE is the longest side of this triangle, and specifically that the length of CD is strictly less than the length of CE. And we know this by the definition of the hypotenuse. But I want you to notice now that in step 5, we've actually gotten what we needed. We started with any other line segment than CE, and we showed that we can always make this right triangle. And when we do that, we always end up with the hypotenuse being longer than CD. So this actually proves that the shortest distance from C to line AB is the lines or the length of the line segment CD. This is exactly what we concluded in step 5. So this proves the shortest distance theorem for us.
All right, the parallel postulate says that given a line and a point not on that line, there exists exactly one line in the same plane that passes through the given point and is parallel to the given line. Here, we have a given line and a point not on that line. A line can be drawn through that point that is parallel to the given line. And the parallel postulate says that there's exactly one such line in the same plane. A different line, even slightly different, cannot be parallel, because eventually it's going to have to intersect the given line. What about lines that are not in the same plane? Introducing skew lines. Skew lines are lines that are non-coplanar, don't lie in the same plane, and also do not intersect. Here, we're given that planes R and W are parallel, and we can think of planes as consisting of infinitely many lines. If we just take two of them, say line DE and line FG, I can see that those lines don't ever intersect, and they're also not in the same plane. And there we have skew lines. Remember that perpendicular lines cannot be skew lines because they're in the same plane, and for the same reason, parallel lines are not skew lines. Check out this three-dimensional diagram with two planes, A and B, and some lines drawn in. Can we identify any parallel, perpendicular, or skew lines? We see that lines P and M are marked as parallel, so okay, P and M are parallel. But we can't say that about any other line pairs because there are no similar markings on the diagram, and we should not assume too much from a diagram. What about perpendicular lines? We see that lines L and N have a perpendicular mark between them, so we can list them as perpendicular. Next, can we identify skew lines? Lines that are in different planes, non-coplanar, and also don't intersect? Lines P and L, those are in different planes, and they don't intersect. They are a skew pair. And also lines, let's see here, L and M, that's another line pair in different planes and don't intersect. And that covers all of the skew lines in this diagram.
In this lesson, we're asking what special relationships exist between two lines or a line segment and a line. And so far, you have constructed parallel lines, you have investigated some properties of parallel and perpendicular lines, and you've even investigated these types of lines in 3 dimensions. Next, what we're going to do is we're going to take a look at what happens when a line intersects a line segment. And specifically, we're going to take a look at what happens when a line bisects a line segment, just like I've drawn right here. The perpendicular bisector theorem tells us about the distance between points along a perpendicular bisector of a line segment and the line segment's endpoints, shown right here. In particular, we already know that a perpendicular bisector must intersect a line segment at the line segment's midpoint, which means that actually that point, which is on the perpendicular bisector, is equidistant from the 2 endpoints of the line segment. Well, the perpendicular bisector theorem actually tells us that all the points on the perpendicular bisector of a segment are equidistant from the endpoints. So for example, if I were to take a point S, then the perpendicular bisector theorem tells me that the distance between Q and S is equal to the distance between R and S, which means that these line segments right here are congruent. I can also take a point that is below my line segment. I could take a point down here, call it E. Well, the perpendicular bisector theorem tells me that the same thing, actually, that the distance between R and E is equal to the distance between Q and E, which, once again, I can draw line segments like so, and conclude by the definition of line segment congruence that they are congruent. Let's go ahead and prove this theorem. Here we are given that P is a point on the perpendicular bisector L of line segment MN. And we need to prove that the distance between P and M is equal to the distance between P and N. Well, we can start by using the unique line postulate. We know that there is exactly one segment between points P and M. Now, after I've drawn that segment, what I can do is I can reflect it across line L. It'll look like this when I'm done. Now, when I do that, then by the very definition of reflection, I know that P is in the image. It is actually just the image itself because it's on the line of reflection. And furthermore, N is the image of M. Furthermore, I know that reflection preserves lengths, and therefore these line segments are congruent. And in fact, we get from this fact that the distance between P and M is equal to the distance between P and N. And that's exactly what we needed. We needed to know that any point along the line L is equidistant from the line's two endpoints. Let's use the perpendicular bisector theorem to solve a problem. Here we're given a diagram, and it has a line segment AB and also a line L. And what we're asked to do is find the length of line segment AC. If we look closely at this diagram, I can see that the distance between A and D is equal to the distance between B and D because those line segments are marked as congruent. Furthermore, I see a right angle marking. So this tells me that the line L is a perpendicular bisector of line segment AB. And furthermore, since point C is a point on line L, I know that it must be equidistant from the endpoints of line segment AB. So that tells me actually that the length of AC is equal to the length of BC. And we can use that fact along with these expressions to write an equation that we can use to solve for x. After we've solved for x, we can substitute it into one of these two expressions, and we'll get the length of AC. So here what I'll need to do first off is combine like terms. And I'll start by subtracting 3x from both sides, and that gives me that x minus 5 is equal to just 2. Now I can add 5 to both sides, and I get that x is equal to 7. At this point, what I can do is substitute 7 in for my expression for AC. And when I do that, I learned that AC is equal to 4 times 7 minus 5, and that's 28 minus 5, which equals 23. So I know now that AC must be 23 units. And furthermore, since AC has the same length as BC, I know that BC must also be 23 units. The converse of the perpendicular bisector theorem is also true. It states that if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So in this example right here, I have line segment MN, and I've got a point right up above it. And this theorem tells me that if the point is equidistant from my endpoints, which by the way means that the line segments I just made would be congruent, then the point is on the perpendicular bisector. So we can actually draw this situation. The perpendicular bisector will pass through the given point, and since it's a perpendicular bisector, it'll be perpendicular to line segment MN, and furthermore, its intersection point at MN will be equidistant from points M and N, which means that these two line segments are also congruent.